Section 12.3 continued here. The determinant of a matrix can help us determine whether the matrix has an inverse, and, if it exists, to find the inverse. So the take note on page 785 talks about the inverse of a 2 by 2 matrix. So if our matrix is A, B, C, D, if the determinant of the matrix A is 0, then it's a singular matrix and it doesn't have an inverse. Okay, as long as our determinant isn't 0 though, then we can find the inverse of A, and again we're going to write it in inverse notation. That's not an exponent, that just tells us it's an inverse. So it's going to be 1 over the determinant of this matrix, and this matrix you're just going to have to know. Okay, A, negative B, negative C, D. And it kind of comes from this fact that we take A times D, B times C, and subtract them, which means we have A times D, and B and C both kind of become negative, and then they swap spots for A and D. So kind of a way to remember it, A and D swap, B and C stay, just become negative because we subtract those. So finding the inverse of a matrix. Does it have an inverse? If it does, what is the inverse? So we check. Negative 3 times 3 minus 6 times negative 1. Negative 9 plus 6, negative 3. It does. Okay, now that we know that, we can use our formula. 1 over determinant times D, negative B, negative C, A. A, B, C, D. So 1 over negative 3. D is 3, negative 6, positive 1, negative 3. Now, this negative 1/3 is our scalar factor, so we take it to each piece. And we end up with negative 1, positive 2, negative 1/3, and positive 1. Again, we took that scalar factor times each thing, so negative 1/3 times negative 1/3 here, times negative 1/3 here, times negative 1/3 here. And then I just simplified. And this is going to be A inverse. Now, does the matrix have an inverse? If so, what is it? 4 times 2 minus 2 times 3 is how we find our determinant of A. 8 minus 6 is 2. Now, to find its inverse, it's going to be 1 over our determinant times D, negative B, negative C, A. We have A, B, C, D right now. 1 over 2 is our determinant. D is 2. The opposite of 2 is negative 2. C, opposite of 3. And A. And this is going to be our scalar factor, so we take it inside to each piece. 1/2, 1/2, 1/2, 1/2. We are going to get 1, negative 1, negative 3/2, and 2. Try B here. Again, find our determinant first. 2 times negative 10 minus 5 times negative 4. Negative 20 plus 20, 0. The determinant of A is 0, which means this does not have an inverse. It's a singular matrix because our determinant is 0. And we can't plug it in as 1 over 0. We can't divide by 0. Same thing here, let's check. 7 times 3 minus 4 times 5. 21 minus 20. The determinant of A is 1. So we're just going to have 1 over 1 D negative B negative C A. And 1 over 1 is just 1. We don't have to multiply through. So 3, negative 4, negative 5, 7. And again, this is D negative B negative C A. Example 5 here is encoding and decoding with matrices. How can we use matrix multiplication to encode the account number from the credit card on page 787? So here we have Bank of Your Knowledge math credit card. The number on the card is 4173 1 2 3 4 9 8 7 6 1 3 5 7. And the coding matrix that they're going to use here is 2, negative 1, 3, 5. It doesn't matter which matrix we use there as long as it has an inverse. We can't use a singular matrix. It has to have an inverse, but we can use any matrix that has an inverse. Okay. Our first step here is to set it up, our card number, as a matrix that we can multiply with. So since we have a 2 by 2 here, we need to have 2 rows. So I'm just going to set it up as 4, 1, 7. Here, I'm going to separate those a little bit better. 4, 1, 7, 3, 1, 2, 3, 4. Put the first 8 numbers. And then the last 8. 9, 8, 7, 6, 1, 3, 5, 7. Okay. We're going to multiply the coding matrix here to get a new string of digits. So I'm going to take our coding matrix times our matrices here. 2 times 4 plus negative 1 times 9. And again, I'm just going to simplify these as we go to save us some time. So 2 times 4 is 8. Negative 1 times 9 is minus 9. 2 times 1. Negative 1 times 8. 2 times 7. Negative 1 times 7. 2 times 3. Minus 6. 2 times 1. Negative 1 times 1. 2 times 2. Negative 1 times 3. 2 times 3. Negative 1 times 5. 2 times 4. Negative 1 times 7. Same thing on the bottom. 3 times 4. 5 times 9. 3 times 1. Plus 40. 3 times 7. 5 times 7. 3 times 3 times 3. 9. Plus 5 times 6 is 30. 3 times 1 for real this time. 3 plus 5 times 1 is 5. 3 times 2 is 6. Plus 5 times 3, 15. 3 times 3 is 9. Plus 5 times 5 is 25. And 3 times 4 is 12. Plus 5 times 7, 35. To simplify here, -1, -6, 7, 0, 1, 1, -1, 1, 57, 43, 56, 39, 8, 21, 34, and 47. That's a positive one, actually, my bad. So our new card number based on this encryption would be -1, -6, 7, 0, 1, 1, 1, 1, 57, 43, 56, 39, 8, 21, 34, 47, which looks like a hot mess. It doesn't look like an actual number of a card, but with this encryption, without knowing what the matrix is, you can't get back to where you started. Now, to undo that and get back to where we started, if you're the card company that's trying to process it, we multiply our new matrix our encoded matrix here by its inverse of our encryption coding matrix. So we had 2, -1, 3, 5. So to find the inverse, we take our determinant, which is 2 times 5 minus 3 times -1. 10 plus 3, 13. Okay, so 1/13 times D, -B, -C, A, which gives us 5/13, 1/13, -3/13, and 2/13. And this is going to be, the inverse of our coding matrix. So this is going to be the matrix that we use to multiply our encrypted card number back to get the original. So we're not going to spend time doing that. We're just going to multiply the same way we did up top. And by now you guys can multiply fairly well, or should be able to. But as you can see, it's almost impossible for a person just to pick the matrix or the inverse that they use. So even if they get the encrypted card number, they're not going to pick, I bet the matrix is 5/13, 1/13, -3/13, and 2/13. That's probably the inverse of the matrix that they use to do this. Fairly safe and secure, because like I said, people aren't going to randomly just pick this matrix to encode. So again, we would just multiply it through and we should get back to our original. Recap here, the product of a matrix and its inverse matrix is a multiplicative identity matrix. Not all matrices have inverse matrices. A matrix has an inverse if and only if its determinant does not equal 0. And there is your assignment.